Okay, hello everyone. So today, just going to give a brief discussion following up on some of the things we've done in the past couple of weeks with respect to making maps and visualizing spatial data. So it's important to remember, as data scientists, we want to try to convey information, whether it's maps or otherwise, as accurately as possible, and that is the information we're conveying matches as best as possible what is the underlying structure of the data. Okay, so for instance, as an example, which of these following maps will tell a better story? We're looking at the counties that voted majority for Obama versus Romney, and we can see from this map it looks that the overwhelming majority of counties voted in favor of Romney, not Obama. And similarly at the state level, we can see more of a half and half split between Republican voters and Democratic voters. And then when we look at another type of map, the bubble chart, we can see that based on population counts, that there's a much larger share of the Electoral College of voters that are voting for Democratic Party, much of them concentrated on the coasts. And many of the red dots in the Midwest are extremely small, suggesting a very few number of voters. So which of these maps do you think is showing the most accurate representation of the underlying data structure? This point is just to highlight the importance of making maps that are accurate, and oftentimes in the popular media and things, other outlets, oftentimes maps are used to distort truth by emphasizing integrity of the wrong element. In this case, emphasizing geography instead of the population density, and this can be potentially misleading to your audience. Another point of issue that often takes place deliberately or unintentionally is with choropleth maps in particular. It can be very misleading depending on how you assign colors to specific segments of the variable that you're plotting. So there's a few different ways to create a choropleth map. As you know, we've normally been just letting R's built-in function to create color codes and assign it to different segments of our variable. But we can also hard code this manually and assign specific colors to specific parts of the variable where we want to visualize spatially. So in this case, there's a few different ways to do that. We can cut our variable of interest into equal intervals, into quantiles, or some kind of geometric function. And we'll talk about the three different ways. So if we look at our variable of median age according to US Census data in 2000, we see a relatively normal distribution of our variable. So if we are to assign an equal interval, we're going to assign colors, specific color to the part of the underlying variable to the data where there's equal intervals between groups. Okay, so here our first group is going to be under 27. Our second group is going to be between 27.4 and 35.4, and so on and so forth, where each width of the data is going to be equal to each other. So some of our youngest people are going to be here, our oldest people are going to be over here, and we can see immediately off the bat there's almost no color that's going to be assigned to this group because there's no real observation or very few observations in the top group here for the older individuals in the census. So if we look at the quantile way to cut our variable into specific groups, what we're going to do here is, for instance, in this case, we have 5 different groups, just like before, but you can see they're not equal intervals. What we're doing here is we're placing a particular share of our observations within a group. So we have 5 groups here. This is indicating that we're looking at quintiles. Okay, 5 groups. The 20% of the data is within a particular group. So 20 times 5 is 100%. So the bottom quintile here, we're seeing the 20% of our median age data. This second very narrow grouping here is going to show another 20% of our age variable, and so on and so forth till we get to the top quintile, where this is the oldest 20% of residents in our census data. And we can see here the darker color is going to be assigned, and we're going to be able to see it in the map because much larger share, 20% to be exact, are actually contained in this color coded category. Okay, there's other ways that geometric or some other way, in this case is standard deviation, which is another way to split your variable. Now, if we have a skewed distribution, in this case, we're looking at the share percentage of multi-ethnic individuals and households in the census. So we can see that the equal interval will not work at all. When we try to have equal interval, 5 different groups, we have a largely single color coded map. Once we get into quantiles, we do a little bit better of a job, but again, we're bunching too much of our data in the top quintile. So in this case, the standard deviation or some other geometric function that allows us to categorize different counties based on different colors will be the more appropriate way to visualize our data. So the rules of thumb for this case is, first rule is just use your common sense. What are your groups representing? Are they meaningful? Are you misleading your audience potentially by using unreasonable breaks for your variable? Binning by quantiles or like quartiles or quintiles or terciles or whatever is typically a safe way to create breaks. And if you're using terciles, you can split your data into 3 groups, low, medium, and high values. If a lot of your data is bunched together, such as you have a skewed distribution, quantiles will not be meaningful, and you'll need to adjust manually or through some other geometric function. If the distribution is skewed, again, you'll need to have some kind of other geometric, like exponential scale. So I think this is important because if you recall from Lab 2, when we were looking at house price to income ratio across the US counties, this was the map that you created. And going back to that map in this lab for this week, we're going to change the way that we cut the variable. For the Lab 2 here, we relied on R's natural built-in function to create this map and color code it. But we want to see if we can cut the variable house price to income ratio in a way that's more conducive to showing variations across the US that maybe are a little bit hidden from this map. So when you go to the lab for this week, part of it will be just rerunning this, remaking this map from Lab 2 and changing the cut function, basically transforming your house price to income ratio from a continuous variable into a factor of so many groups, of n groups that you specify, and you will assign a color to each group. And then you'll compare and contrast and see how best to cut the variable. Okay, so at this point, you can continue on to the lab.